Hello, welcome to the NYU Tandon School of Engineering and the latest presentation in our seminar series in modern artificial intelligence. The series is aimed at unifying scientific communities around the influential research ideas of today that we predict will have a major impact tomorrow. And we hope that the discussions that result here will promote groundbreaking discoveries and contribute to building a better world. I'd like to thank Daniela Kovacevic for her strong support, as well as my own Department of Electrical and Computer Engineering for hosting this series, which has evolved since its launch into a respected and significant event in the AI world. When I first conceived of the series, I hoped that I would be able to attract highly esteemed speakers doing revolutionary work in their respective fields. I've mentioned this before, and I'll say it again. With some humility, I've succeeded beyond my wildest dreams. Look no further than today's guest for proof. Arthur Gretton earned undergraduate degrees in engineering and physics from the Australian National University before earning a PhD in machine learning from Cambridge in 2003. He is now a professor with the Gatsby Computational Neuroscience Unit and a director of the Center for Computational Statistics and Machine Learning at University College London, as well as a research scientist at Google DeepMind. His recent research interests include causal inference and representation learning, design and training of generative models, and non-parametric hypothesis testing. And his CV also includes stints as an associate editor at IEEE Transactions on Pattern Analysis and Machine Intelligence and an action editor for JMLR. He has been a senior area chair for both the Conference on Neural Information Processing Systems and the International Conference on Machine Learning, and he has served on the program committee of Association for Computational Learning's Conference on Learning Theory. Since January 2020, he has been a member of the Royal Statistical Society Research Section Committee. I could go on, but if I continued listing all the programs he has chaired, workshops he has spearheaded, and tutorials he has organized, we might not be hearing his presentation until the wee hours. That presentation is entitled Learning to Act in Noisy Contexts Using Deep Proxy Learning. In it, he will explain how proxy causal learning can help us evaluate the expected outcome of an action or policy using off-policy observations of user actions, where the relevant context is noisy, anonymized, either because of privacy constraints, data bandwidth restrictions, or the intrinsic properties of the setting. I know none of us can wait to hear from him. So without further ado, I give you Arthur Gretton.
Thank you for the kind invitation and these nice words. So I'm going to talk about learning to act in noisy contexts using deep proxy learning. I like to get questions during the talk, so please don't hesitate. If anything's not clear at any point, raise your hand or yell at me, and I'm going to do my best to answer. The course is going to be on causality, but it is self-contained, so everything should hopefully be clear from the context. So I'm going to just start by introducing a simple toy example, which is going to introduce some variables and some ideas, some concepts that we're going to need. This is a simple Simpson's paradox style example. In this setting, we've got X, which is a disease severity. So I've got either a mild form of the disease or a severe form of that disease. And what we're observing here is the way that this disease is being treated in a particular hospital. So in this hospital, the doctors look at the severity of the disease, and then they decide on a treatment. So that treatment might be you give pills or surgeries. Pills more likely for mild, surgery more likely for severe. And from that treatment and from the severity, we get an outcome that the patient is cured or not. And what we've observed historically from this hospital data is that the chance of being cured given pills is 0.85, chance of being cured given surgery is 0.72. So where do these numbers come from? They come from this equation up here. And it's important when you're looking at this equation to understand the process that's going on in the hospital in order to bring us to that equation. So let's say that we observe that pills were given to the patient. Now we know that the doctor is more likely to assign pills when the disease took a mild form, right? And so what we're going to do, we're going to take the chance of being cured given the treatment and given the severity, and we're going to upweight it by X given A. So basically more likely that the disease is mild, less likely that it's severe, given that we saw that pills were assigned. Conversely, let's say that we saw that surgery has been assigned, right? Well, then it's more likely it's a severe form of the disease. So we'd upweight the severe form, downweight the mild form when we take this average. So this is what we've observed historically. This is the policy that's been followed historically in the hospital. Now let's say I'm a hospital administrator and I look at my budget and I say, well, pills are cheap, pills work better, everyone gets pills. So now I'm intervening on the system. I'm imposing a new policy. Let's see what happens when we do that. So graphically, how am I going to denote this? This little a with the double boundary is my intervention, and it's a very simple intervention. It's everybody gets pills. And the y superscript a is the random variable y resulting from that intervention. What we notice graphically from this notation is there's no direct arrow from x to this intervention. So it's everybody gets pills. It's not everyone gets pills if they're not too sick. I'm keeping on my graph this historical a. This is what the doctors used to do, but that's no longer influencing my outcome. Okay, this is just what I've recorded from the past. So what do we get when our hospital administrator makes this choice? Well, we get the following results. The probability of being cured under the intervention pills is 0.64. Chance of being cured under the intervention surgery is 0.75. How do we obtain these quantities? Well, we've got the same conditional mean of being cured given treatment and severity, but now we're just taking the average over our population. So we call this the average causal effect or average treatment effect. It is basically the effect on average of doing a particular thing, which is in this case, giving a particular medicine. All right. And so you can see that, once you've shifted the policy from the policy used in training, or once you've intervened on the system, depending on what language you'd like to use, you're getting a different answer to the answer that you got in the past. All right. So what might happen, though, when we don't see this context? So it was very important in understanding what was going on to be aware of the context in which we're making our decisions. But let's say, as very often happens in practice, the doctors don't record, in granular detail everything about the patient and their illness. Let's say that the doctors are treating the patient based on what they've seen. They've interviewed the patient. They've run a bunch of tests. They've been, very careful in assigning treatment. But then, let's say what the doctors have recorded is just somehow an incomplete, noisy view of this X. So in this case, W is whether there's a fever or not. Okay, so the doctors are acting based on X, but they've recorded W. W is what we get to see that informs us of what the doctors were deciding. Now, I've set this example up in a particular way, which is that the W, it's binary valued, it's fever or no fever, and it's a pretty decent indication of the severity of the disease. So basically, probability of fever given the disease is mild is 0.2, probability of fever given the disease is severe is 0.8. So, okay, it's not exactly X, it's a noisy view of X, but it's not too bad of a noisy view, right? It's like, surely it should be good enough. So the question now becomes, could we treat W as if it were X when we're trying to find the average causal effect? So before we'd sort of have, Y given A and X and P of X, right? But now we're treating W as if it were X. What's the worst that could happen? Like W is pretty clean view of X. It's not too noisy. Can we get away with this? So as always, with rhetorical questions in talks, the answer is no. And in fact, we flip the answer from what it should be. And in fact, our average causal effect when we're using W as if it were X is actually telling us that pills are much more effective than they actually are. By the way, the numbers here are not through some sort of exhaustive parameter search. They were the first numbers I got. So it's not that this is an edge case. This is actually something that can come and give you difficulties quite widely. Moreover, unless you observe X in training, Judea Pearl showed back in 2010 that it is impossible to identify the average causal effect with W alone, right? Because what's going on here, if we don't see X in training, is unknowable. And because it's unknowable, we don't know what's going on with X, and so we can't anticipate, the effect of X when we're doing the average causal effect. All right. So this is the problem we've set ourselves. We've got a situation where we've recorded people acting in context, but we don't get to see the context. We just get to see a noisy version. And the purpose of this talk is to tell us what we might do in this circumstance. All right, there are going to be some ground rules. So I'm going to give you the ground rules before I give you the talk outline. the ground rules are as follows. This thing here, it's got a really messy name, the stable unit treatment value assumption. What does that mean? All that means is that the pill I take doesn't cure you. Okay, so whatever treatment I have doesn't affect my neighbor. So this is an assumption we're going to make for this talk. It's not always true, but we're going to assume that it's true. What does this one here say? This one here says that, what if there was another hidden V here, which I had no idea about, affecting these guys? I'm not going to allow that. So I'm going to basically say, like, everything that's hidden is something that I'm aware of in one way or another. Okay. Final assumption is overlap. So imagine we never gave pills to people with a severe form of the disease, or we never gave surgery to a person with a mild form of the disease. In that case, we'd have no idea what's going to happen, right? We're asking a question about something that we've never seen. So we're not going to allow that. Okay, so those are our ground rules. Great. By the way, any questions at any point, please don't hesitate. Yeah. Okay, we've got our ground rules. Let's now move on to our outline. Okay. So I've said at the outset that it's impossible to identify an average causal effect or average treatment effect using hidden covariates without seeing them in training. If you're just looking at noisy views of those covariates, that is true. It's mathematically true. But it turns out that with a bit of additional information, it is possible. And how much additional information is what we're going to talk about in this talk. So application areas, I'm going to talk a bit more about these in a short time. But situations where the context in which the user is acting is privacy constrained. So example, I might be looking at my emails and I'm acting based on those emails. But if I'm looking at, if I'm a large company and I'm trying to aggregate a lot of people's emails in order to make better email prioritization software, I will only be looking at anonymized versions of those emails. I won't get to see what the user sees. So this is one constraint. Another constraint, if you've got edge computing, so you've got an edge device, it's gathering a ton of data, but it only sends in a summary. Obviously, the summary is an incomplete and noisy view of the data that it gets to see. A third scenario is where there's just a fundamental limitation on what you can record. So let's say my internal state of mind is something that it's very challenging to view directly, but maybe from quizzes or from tests or so on, you can get some idea of it. So it's sort of like there is a truth, but then you get to see only a noisy view of that truth. And I'll talk a little bit more about a specific example. What are we doing in this talk that's different from what's gone before? So the paper on proxy methods for causal learning was published in 2018. The methods that I'm going to talk about today address is the case where all of our treatments, our contexts, et cetera, might be very high dimensional, very complicated. So in this case, let's say our treatment is not just like I give a pill or I don't give a pill, but it's the output of a large language model, like I'm making a suggestion for some sort of aspect of one's life. Or it's the output of a diffusion model, like I'm making an image for an ad. In this case, the treatment that we're posing is actually very, very complicated, and we need good neural net features that we learn in order to determine the effect of that treatment. And likewise, the context might be high dimensional, might be very complicated, and we're going to have to learn features of that context in order to determine the effect of our actions. The final point, and that's going to be clear from the talk, and I'm going to repeat it at the end, is don't meet your heroes. So the models that I'm going to talk about have latent information, right? This X is hidden, it's latent. Now, it's important that that hidden X be there, but we should never attempt to recover it. So this is not like an autoencoder or nonlinear ICA where we're trying to recover these latent variables. We use the fact that they're there, but we don't try to find them. And so that message is something that I'm going to sort of repeat in this talk. Right, so that's our outline. So what are these proxy variables? What information is going to end up being sufficient in order to recover the average causal effect or recover the effect of actions in context from purely observed data? Okay, so we've seen what doesn't work. Let's see now what does. I'm going to give two examples to illustrate this. This is also by way of sort of describing what it is that proxy methods are good for. Like, what problem is it that these solve? Or I'm going to give a couple of problems that they solve in order to sort of like encourage people to use them and to understand what they do. All right, so let's start with the email example that I mentioned briefly earlier. Let's say that I've got X. X is my email contents, my inbox. And then my user is going to go and prioritize important emails. And then from prioritizing important emails and the contents of the inbox, they're going to get a good result. For instance, that they've answered the emails that they need to answer on time. Okay, so this is some measure of user satisfaction about how well they've dealt with their emails. Now, let's say that we, as a large company, are interested in flagging important emails to the user in advance so that they can deal with their emails more effectively. But we might not be allowed to look at the de-anonymized contents of the emails. What we might be allowed to look at here, and you can sort of see a little bit blurry an image here, is anonymized email contents. Okay, so what we see here is the W, which is the contents of these anonymized emails. And I'm sort of seeing that at the start of the day before the users dealt with any of these emails yet. All right, so that's my W. Now, we've already demonstrated that using W as if it were X is not a good idea. So we need to do something else. What do? We're going to need additional information. And this additional information, Z, I'm going to say this is the contents of my anonymized email inbox after the user has taken their actions. And so it's by the change in this anonymized inbox content that I'm able to determine the effect of the actions in context. So basically, the way that this changes from here to here, under some assumptions, and we're going to go into quite a bit of detail about those assumptions. So nothing's ever for free. But under some assumptions, we're able to then identify the causal effect of A in context X, without actually seeing X. So seeing only the noisy inbox before and the noisy inbox after the user action. Yep.
What's the meaning of the anonymized inbox? Like, what could be the change? Could you give an example? Because my understanding is that probably user can sort this email according to their prioritized. Like, what it actually got changed from W to?
Yeah. So here I'm being deliberately ambiguous, but a way to think about it is that the contents of the emails might be, let's say, scrambled. Like maybe some salient factors will be removed, or usernames will be redacted. Maybe that general idea. There is, of course, a challenge in trading off how aggressively you remove information with how effectively you deal with the emails. In respect of the noise assumptions being made, I'm going to talk a bit more about those soon, so that might also help clarify. Yep. Mm-hmm.
Is the intuition sort of that you're looking at the actions that the user would have taken if it's not X, or if it?
Yeah, no, that's a very salient question. So basically, like what the user gets to see is X, right? I get to see my email inbox. But Google is going to try and make a new policy to prioritize important emails, in aggregation over many, many, many users. But what do they get to see for each user? They only get to see W and Z. They don't get to see X. So we know the user is acting with X, but we only see the noisy version of what the user sees. And from that, we're trying to evaluate the new policies that we might perhaps explore. Yeah. Yep.
The action is made by the user itself or the software.
So right now, the user is taking action depending on X, but we might want to, basically automate or show a way of prioritizing important emails. Yeah. So we're going to try and reproduce or even improve on the actions that the user does. Yeah. Yeah. So this is an example. And what we can recover is this average causal effect from observational data. So let's understand what the average causal effect is here, because it's actually not very useful, right? Average causal effect, remember, this is like if I take an action A, what is the average outcome? But taking a fixed action without looking at the context is not really what we want to do here. This would be like, what if I had software that always highlighted the first email on the inbox without looking at the contents of the inbox? You could do that. I don't know if that would help anybody. Yeah. So I'm going to focus in this talk on average causal effect just because notation is the simplest thing to do. But using the tools that we're developing in this talk, we can also address some more interesting questions, like we have a new on-device policy, right? Which takes an action A conditioned on the contents of the inbox. And this is much more likely what it is that we're going to do. Now we want to evaluate the effectiveness of this on-device policy based on all of the sort of emails that we've gathered from users acting, off policy in the past. And this is one of the things that we're going to be able to do using the tools that I'll describe today. So this is a much more interesting scenario. All right, so this is the case where we're trying to act in context where we don't see the clean context, but we just see noisy versions for privacy reasons. So privacy preservation is, absolutely one valid scenario for these proxy methods. I'm going to give a second example where it's like there is an unknowable ground truth. Okay, and so this is in a fitness tracking example. So let's say that we have X, which is like how fit I am, right? And then I'm going to try and take some actions, which in this case is either cycling or swimming, in order to obtain a goal, which is maybe I'm going to like run a half marathon and get a good time. All right. Now, I'm not an Olympic athlete, and so I don't have the resources to get like VO2 max on a treadmill with a face mask and all of that stuff, right? So my knowledge about my current health is not at a sort of very high granular level. And most people don't have the resources to do all of the scans and fitness measurements in order to get like a view of one's body at that sort of granularity. But what you might have is a Fitbit, right? Something that gives you like a pretty decent idea of your resting heart rate and whatnot, but absolutely doesn't replace a full scan that an Olympian would get. Okay, and so what we might have is we might have a series of readings of our sort of state of body before doing the fitness regime, and then we might have these readings after the fitness regime. And obviously, there's been some change in the underlying health, which we're using these as noisy proxies for. And then we gather that data, and then we might then want to recommend to users based on the data we've gathered what fitness regime they should take in order to achieve an outcome. So yeah, in this case, the noisiness arises just because this X, it's just not possible with most people's resources to find it. But you can find cheaper, noisy versions of it. But the sort of principle that I'm describing is very related to the principle with the emails. Yeah. So any questions about these ideas? Great. Okay, so I've sort of said, what it is that we're doing. Now it's time to say how it is that we're doing it. And in particular, like, these W's and Z's are noisy views of X. And I've sort of waved my hands and said, oh yeah, they're noisy, like we'll figure it out. So now it's time to understand actually what it is that we need to assume about W and Z in order to recover the effect of X in context A, right? Because obviously nothing's for free, so we have to make some assumptions and requirements. And we're going to now look at what these might be. All right. So here is a general purpose graph. It's got a few more edges on it than the ones I showed before, which encodes some of the assumptions that we're going to make, or some of the assumptions we're going to make about our variables in order to recover the effect of X or actions in context X. Okay, so X is the confounder. We don't see it. I'm going to call W the outcome proxy. So this is a variable that can influence Y, but has no direct connection to the action A that we take. And then we've got what we call the treatment proxy, which can interact with A, but doesn't have any direct effect on Y. And so this structure is sort of imposed in the examples that I gave before by the fact that time goes forward. And so W happens before things, before the actions, and Z happens afterwards. But obviously, this graph allows for more complex interactions. I should also say that this arrow here with the double edge, what that means is I take no position on the causality between X and W. So it could be X causes W, could be W causes X, could be there's a hidden common cause. We don't know, we don't care. There just is some link between these. Likewise here, in the examples I gave, A causes Z, right? The action I take causes how fit I am next month. But I can also consider cases where there's errors in the other direction. I won't for this talk, but just keep in mind that I can deal with more complicated scenarios than the ones that I spoke about in the examples. But here are the core assumptions that we do need to make, okay? W here is separated from Z and A by X, right? X is kind of a bottleneck. It's a low-dimensional bottleneck separating W from ZA. Likewise, y separated from z by ax. So ax bottlenecks y from z. These are the assumptions we do need to make. So I'm color-coded them, and this color coding I'm going to use for all of the rest of the talk so you can quickly see what group of variables I'm talking about. So I've got the orange assumption, and I've got the purple assumption corresponding to those groups of variables. These are the assumptions we're going to make structurally on our variables in order to recover the effect of A under X. All right. So it seems mysterious, right? W on its own was not enough to recover the effect of X. W and Z together are enough. Like, why is that? Because that's not obvious at all. Okay, so I'm now going to prove to you in a simple setting why it is that W and Z together allow us to recover the effect of action A under context X. So let's begin with what we already know, which is this average causal effect, where I take my P of Y given X and A and integrate it over X. In the example I'm giving here, X is categorical, so it takes one of the X values, and I'm just going to sum over the probability of each of the values that X is allowed to take. So, severe disease, mild disease. I'm going to use a slightly more concise notation for this, which is I'm going to write this as a matrix vector product. So what is this matrix? This is the matrix of probabilities of Y, because Y is also categorical, so it can take one of, let's say, dy values given X, right? So X are the columns, Y are the rows, and this is a dy by dx matrix. And then I multiply that matrix by this vector, which is a dx by 1 vector of probabilities. This gives me my average causal effect, my average treatment effect, the average probability of Y under intervention A. Okay, so this notation is going to be a little bit easier to follow. Our goal is to get rid of the blue, right? If my equation has any blue in it, I have my hidden variables. So I need to get rid of that. Okay, and once there's an equation with no more blue, then I've won. Right. So let's begin by putting W into the mix, right? And let's say that let's pretend for the moment we can observe X and that we can solve the following equation. This equation maps the matrix of probabilities of W given X to the matrix of probabilities of Y given X, okay? And this is a dy by dw matrix. So in order to solve that, there are constraints, right? We're going to need to take a pseudo inverse of this, which means that we're going to need that dw is greater than or equal to dx, and we're going to need that this has, the rank dx, right? So this is another way of saying that, w has to be of dimension at least dx or bigger, and that it has to have a complete view of x, right? So there can't be dimensions of x that I don't see, but which are relevant to predicting the action of A and Y. So we've already started to make an assumption, which is, it's not that W is a clean view of X, it's a noisy view, but it can't be missing any of the bits of X in it. Yep.
Does it also assume the linearity of this relationship?
Right now, exactly. Like I'm just talking about categorical variables, tables of probabilities. We're going to get to the continuous variables, in the second part of the talk, yeah. But absolutely. So this is required, yeah. Okay. So let's pretend, okay, we're going to pretend we've seen X. We're going to solve this system of linear equations. We're going to get our H, okay? What happens then? Okay, let's say I've solved for my H. I've made the assumptions I need to make. What happens next? All right. Well, this is my average causal effect. This is from the last slide, Py given XA integrated over P of X. I'm going to substitute this equation in, right? Just pop it in here. And now I notice something, right? PW given XPX is just marginalizing PW given X over PX, which gives us PW, right? Here it is. Now, there is no blue in that equation, right? So if I were able to solve for H, I could get the average causal effect by treating W as if it were X, as long as I switch Py given XA to this green matrix. Okay, so that's interesting, but it has required me to solve an impossible problem, so it's not that interesting. Okay, so where do we go from there? So let's now take another step. Are there any questions about this before I do that? Okay, let's take the next step. This is from the last slide, right? I've got Py given XA, I've got PW given X, I've got this matrix here, which I've potentially solved for, but this equation has blue in it. So now I'm going to project both sides of this equation on a matrix. that matrix will be P of X given ZA. So for every A, I have a different dx by dz matrix. Okay, I'm doing this for every action that I can take separately. So I get a different matrix, obviously, for each action, right? Project this side on Px given ZA, project that side on Px given ZA. What I need to make sure is that I don't increase the null space of my system of equations by this projection. So now I'm making another assumption. What is that assumption? Well, this thing here, dz has to be greater than or equal to dx, and the rank of this matrix has to be dx, same as before with w given x, right? I'm not allowed to basically lose anything by this projection. So this tells me, again, I need to know something about my z. It has to be greater than or equal to dimension x, needs to be able to see all of the x, but it doesn't need to be a clean view. It can be a noisy view. Right. Okay, so we do that projection on both sides. Now what happens? Well, now I start using the orange and the purple assumptions. Okay, let's start with the orange assumption. I know that W is bottlenecked from ZA by X, right? So this projection means that I marginalize over X, and that gives me PW given ZA. There's no blue in that equation, right? Now let's use the purple assumption. Okay, Y independent of Z given AX, so Y bottleneck from Z by AX. Again, this marginalization just means that I'm marginalizing over X, and that gives me PY given ZA. Again, no blue. So substituting both of these things in, and I get PY given ZA is HPW given ZA. Subject to all of the rank assumptions that I made and dimension assumptions that I made, this allows me to recover the average causal effect, right? Using purely observed data. Why does it allow me to recover the average causal effect? Well, let's remember where I used H a couple of slides ago. I used it here, right, to get the average causal effect. Any questions? Yep.
So what happens if the DZ is smaller than DX?
Yeah, I mean, if DZ is smaller than DX, then this doesn't work. What you might still be able to do under some assumptions is like think about like a range of causal effects that you might get. Yeah. But you know, at least in this case, you're no longer able to nail down the average causal effect. You're perhaps going to start making assumptions. Yeah. And under those assumptions, you're going to get a range of possible causal effects. Yeah.
DZ is equal to DX.
That's okay as long as this matrix is invertible, right? So yeah. Any other questions? Great. Okay. So that's fine, right? But in the real world, maybe I don't have like categorical valued variables. Maybe in the real world, I have, you know, emails, or I have some, you know, recommendations for my fitness and so on. These are complicated things. I now need to sort of take these ideas and think about how I might instantiate these for proper data that people care about. Okay, so this is now going to be my focus. Okay, there are two ways that we can do this. So we can use fixed dictionaries of, well, fixed infinite dictionaries of features. So that's this kernel approach. Or we can use finite dictionaries of adaptive features, which is the neural net approach. The code for both methods is provided here. So the kernel features were done by these super talented group, Afsane, Yushen, Limor, Anna, Ricardo, Matt, and Krikamal. And then the neural net features by these very talented students, Liwan and Heishiro. For this talk, I'm going to focus on the neural net features, but you can use either. But for the purposes of this talk, I think the neural net features are going to be the more interesting ones because they allow you to sort of adapt to very complicated data. So let's stick with those. All right. For the remainder of the talk, there is one model and one algorithm. So that's all you need to remember. What is my model? Well, it's a neural net where I've considered separately the linear final layer. Okay, so I've got a bunch of neural net features and a linear final layer, and that's my function. So all my functions are going to be of that form. Why bother setting out the linear final layer as a different thing? We're going to see. There are two reasons. One that I'm going to show you on the next, next slide. Which is a bit unexpected. And then the second reason, which is that this is a core assumption required to make any of what I say work. Okay, finite dictionaries of linear, linear combination of finite dictionaries, and the theta are the parameters of the neural net features that we're going to learn. Okay, so that's our model for the rest of the talk. Okay, there is one algorithm, which is ridge regression. So again, for the rest of the talk, you only need to know ridge regression. What am I doing? Oops, oh, that's interesting. Let's go back to that. Right, I'm taking my linear combination of features. So in fact, I think this notation is not great. So I'm going to use gamma transpose by theta xi. So please ignore this notation here. So linear combination of features, I'm predicting y from that linear combination of features. And I'm giving a penalty, like an L2 penalty for my linear final layer, which is kind of handy for stability. Okay, so this is how I'm going to learn my neural net features and my linear final layer. Now, what's interesting about this is that given the features that I've used, I've got my linear final layer in closed form. Right? So given, fixing theta, this is the equation that describes my linear final layer, right? It's the cross covariance between y and the features of x, and the covariance between the features of x and themselves. And then I can plug that in. Okay, so I needn't do this, right? I could just do SGD on everything with this loss, but I'm not going to. And so this is the first reason to separate out the linear final layer, which is the bonus content for this talk, which is what we're going to do. We're going to take this closed form expression, substitute it in, and then backprop through the Cholesky method that we use to solve this. So we don't actually do the inverse, we do Cholesky decomposition in order to learn the theta, right? But we use this sort of fixed expression of gamma as a function of theta in order to learn the theta, rather than doing SGD on gamma and theta together. So is that clear? So why do we do that? Like, why use this closed form expression for gamma and then substitute it in and then backprop through to get theta? Why not just do SGD on gamma and theta together, which works, right? What's interesting is that using this expression for gamma actually results in a much faster optimization than doing SGD on gamma and theta together. So substituting in the expression of gamma as a function of theta and then doing SGD on theta works better. Okay, so number of epochs, mean squared error, smaller is better. This is doing that approach. This is just doing SGD on everything. So I don't know if this is kind of obvious to everyone. We were surprised to have found it. So I encourage people to sort of figure out what's going on here. My very hand-wavy explanation of what might be going on is that, what the linear final layer kind of does is to, decorrelate the features and then covary them with the labels. And so basically, like adjusting, gamma and theta by tiny amounts to maintain that decorrelation seems to be less effective than saying, well, look, I know what gamma is going to look like as a function of my theta. So let's just use that and only do the SGD on my theta. So that's a conjecture as to why it is that this Cholesky approach is so much more effective. But this is not a formal conjecture. This is me just speculating. But I'd really be interested to hear your thoughts about that. So this is bonus content. This is not core to the talk. There's a second reason we're going to use the linear final layer, which is that everything that I do requires it. And we're going to get to that point soon as well. So any questions about that before I go on? Okay. So we have now our model. We've got linear final layer and some neural net features. We have our loss, ridge regression. Now we're going to give the method, right? So first of all, what do proxy methods look like for continuous variables? I'll describe that. I'm going to then give the loss function we're going to minimize in light of what the proxy method looks like for continuous variables. And then I'm going to define the ridge regression solutions in order to solve for that. Now I say solutions plural because I'm going to need two different neural net ridge regression methods in order to solve this. So like again, I'm going to need two neural nets to solve this problem. Luckily for us, it's a min-min problem, not a min-max problem. So it's not going to have instability issues or anything like that. But it is required to have more than one neural net. And each of those has a task to do. The colors indicate what those tasks are going to be, but I'm going to get to that shortly. Right. Okay. So this is what the average causal effect looks like in the continuous setting, right? So I've got my E of y given ax, I integrate it over P of x. we don't observe X. So what might a proxy relationship look like in this continuous setting? Here is what it looks like. So I've got this H, but the H is now a function of Y of W and A, and not a matrix. Okay, and then I take the conditional mean of that function, E of W given AZ of this, and then I get E of Y given AZ. Right. So basically, the matrix product that we did before, we're now expressing as an expectation, which in fact is exactly what it is, in order to map from W given AZ to Y given AZ. And this H function is what does that transfer. We're going to call it the link function because it links W given AZ to Y given AZ. Right? And then once we've got this link function, we can compute the average causal effect using W rather than X. All right. So I'm going to call this conditional Y given AZ the primary conditional mean. I'm going to call this one the secondary conditional mean for reasons that will be apparent shortly. But you can see in this equation, there's no blue, so I don't need to observe or even model X in order to solve it. There are conditions. The conditions are analogous to the conditions we had in the linear algebra case. Notationally, they're messier, so I'm not going to clutter my slides with them, but look at the papers. But the intuition you got from the linear algebra case is the correct intuition for this continuous case in terms of W and how it relates to X and Z and how it relates to X. All right. Once we've learned H, this is going to be our average treatment effect. And you can see that we're integrating over W, whereas before we integrated over X, everything's observed. All right. So we need a loss function, which if we minimize that loss is going to give us this answer. What's the loss going to be? Okay, so that's for the next slide. Okay, this is our goal. So this is from the previous slide. I'm mapping W given AX to Y given AZ, sorry, W given AZ to Y given AZ using a link function. Now I'm going to claim that this square loss is the loss I need to minimize in order to solve for H, right? Minimizing the squared difference between Y and the conditional mean of W given AZ of my link. So why is that, right? Well, let's forget about this for a moment, okay? Let's just think about good old least squares regression. Let's say that I'm mapping from FAZ, some function of AZ, to Y with a squared loss. Well, the F that solves this, that minimizes this, is the conditional mean of Y given AZ, right? This is like classic statistics. Okay, so if I wanted a function that minimized the square loss, I would have the conditional mean. However, I've just said that I know the form of my conditional mean. I've said that my conditional mean has to be the conditional expectation of H, right? So all that I've done is taken this F, substituted this form in there because I've said it had to take that form, and that's it, right? So the reason this is my loss is because I've said the conditional mean of Y given AZ must take the form of this mapping of H. So that's it. That's all that there is. Questions? Great. Okay, so this is the loss that I need to minimize over H. Next is I need to parameterize H, right? What form does my H take? So here I'm going to be a little bit tricky, okay? I'm going to say that H, which is a function of two arguments, is going to be a linear combination of neural net features, but I'm not going to just use a single dictionary of neural net features of A and W. I'm going to do the following. I'm going to take a neural net feature dictionary of W and a separate neural net feature dictionary of A, and then I'm going to take a big long vector of all pairwise products of those features, right? So this is the way that I'm going to parameterize my function that I'm going to then plug into that loss that I'm then going to solve to get my answer. So looking at this, right, you might be asking, like, why on earth did Arthur just do that, right? So why did I use this big long vector of pairwise products of features? Why not just a neural net, right? Why do I treat my linear final layer separately? So pretend you didn't see the slides from before. Why would I make this as a modeling assumption? Okay, and it turns out that both of these things are necessary, and we're going to see it in the next slide. So I'm going to tell you why this pairwise vector of products of features is necessary, and I'm going to tell you why this linear final layer is necessary. Both of them are necessary for what I'm going to say to work. Okay, so remember what we were trying to solve. We're going to try and solve ridge regression because there's only one algorithm in the talk, which is ridge regression. We've got our conditional mean of h y here, which is our conditional mean of y given az, given our parameterization. I'm going to put this ridge term here, which stabilizes our final layer. Now, this is different to normal neural net regression, right? Normal neural net regression would just have an h here and nothing else. But now I've got a conditional mean of h as my input. Well, that's weird. So how do I do that? Okay. Now, there's a bunch of ways we could do that. And I'm going to start with one way, which actually does work, which is I will learn a generative model, right? I'll learn a generative model that takes A and Z and then generates samples of W. Right? And these are all things that I see. So I'm going to learn whatever my favorite model is, a diffusion, and yeah, whatever I like. I'm going to generate samples of W given AZ. I'm going to take that sample average here, and then I'm done, right? That works. Why wouldn't I do it? Well, imagine that W and A and Z are super high dimensional. I can learn a model to sample these very high dimensional densities, but it seems that in doing so, I'm solving a harder problem than I wanted to solve, right? All I wanted to do was take this conditional mean. And now suddenly I have to learn like to generate, W, which might be like super high dimensional text or like demographic information or what have you. That seems hard. Why am I solving a hard problem? Right? When in fact, thanks to the parameterization that I introduced on the previous slide, I can solve an easy problem. Okay, here's the parameterization from the previous slide, right? I'm saying my H is a linear combination of this pairwise product of features of W and of A. Now I need to take the conditional mean of these. So I do, right? Conditional mean, conditional mean. And now I notice that thanks to my parameterization, I can take that mean inside. And all I need to do is get my conditional feature mean, my conditional mean of the features of W that I need to predict my Y. So I don't have to learn to generate samples of W. All I need to do is to get the conditional mean of the features that I'm going to use to do my prediction. Much easier problem. And in fact, there's one algorithm, right? I'm going to do that with ridge regression. One algorithm, right? So I'm going to do ridge regression to learn this final linear layer here, okay? Now the linear layer here is a matrix, not a vector. Why is it a matrix? It's because I'm mapping from features of AZ to features of W, right? So my output is now a vector, it's not a scalar, but then I just have a linear final matrix rather than a linear final vector, all right? The other thing is this linear final matrix is explicitly a function of these features, right? I keep this explicit. What does that mean? That means that if I tweak my features, if I change my theta, this remains correct. I still have a correct conditional mean, right? Which is very important because I need a correct conditional mean in my loss. So using this linear final layer allows me to maintain a correct solution of my secondary problem, of my orange problem, when I'm solving in my primary problem for this theta. So all of this parameterization has a purpose, and this is the purpose. Questions? All right, so what I'm going to do, here is the final algorithm. I'm just going to put it all up on one slide so you can see what I'm doing. First of all, I solve for this secondary regression problem, which gives me my conditional mean and my features of W given AZ. Okay. I can do backprop through Cholesky to adapt the features of my secondary regression to get good features of A and Z. Once I've solved F, I plug that in my primary problem, which is the one that's predicting Y. Okay. I solve for my linear final layer, then I backprop through Cholesky to get theta and psi. And remember what I said on the previous slide. The key point is that this conditional mean remains correct even as I adjust my theta features, even as I adjust my features of W that I used in my secondary problem as outputs. All right? And then what I'm going to do is I'm going to alternate between my primary features and my secondary features. So I'm going to alternate adapting my secondary neural nets and my primary neural nets until I get convergence. So this is a min-min problem. It's not going to be one of these adversarial ones where there's instabilities. It's going to behave itself. All right. So this is the algorithm. This is it. Okay, so ridge regression and a little bit of trickery. Okay, the key point is I'm not learning to map to all of W. I'm not learning to sample all of W. All I'm doing is learning conditional means of relevant features of W. And these are relevant because my primary regression has learned them. So this is an easier problem. All right. Great. So in the remaining minutes, I'm going to just show some experiments. And these are going to demonstrate, I think, the principle that like trying to explicitly learn your latents and model samples of W given those latents is a hard task. Whereas the approach that we're going to take is going to be an easier task and is going to work better in the settings where W is high dimensional, my actions are high dimensional, everything's hard. Okay, so let's say that I've got X, which is some properties of a sprite, and then my treatment A, which is the sprite, right? So my treatment A is now an image. So imagine my treatment was like an ad I wanted to show on the web or something of that nature. So something high dimensional, complicated. I'm going to make W as well an image. So W is also high dimensional, complicated. I'm going to force myself to learn some good neural net features to solve this problem. And then I'm going to try and find the average causal effect for this action, which is an image. Now, on this graph, I've got different data set sizes. A lower is better. That's my error. What I'm showing here is approaches that don't use adaptive neural net features, but still solve this proxy problem. And then an approach that does use neural net features, and it's going to do better. So no surprises. But then I've got something up here. And this one is interesting. So this is an autoencoder approach. What it does is it looks for looks at your W, your A, your Z, etc., and then tries to learn explicitly a latent representation, which it can then sample from. So it's trying to solve a harder problem because the autoencoder doesn't know what it wants to do with its latent representation. And so it's just trying to reproduce the whole world in order to solve what amounts to, in fact, a much simpler problem, which is causal effect estimation. And so because it's trying to solve a harder problem, it struggles in this particular setting as compared to our approach, which is targeted towards the task that it's trying to solve and doesn't explicitly try and make this latent representation. So this is what we're finding here, that we have actually got quite a big performance improvement over the autoencoder approach. So sometimes learning the latents helps, but it's something that you're betting on, and it isn't always true. All right. So any questions about this? Okay. Since we're coming to the end of our time, I mean, we've also done like a policy evaluation experiment where, again, using neural net features improves over using non-neural net features. So I'd encourage you to see the paper for details. So just to sum up, right? I'm learning to act where I've seen training data where the context of the user was hidden, okay? So the user is acting in context. I don't see the context. I just see noisy versions of the context both before and after the user action. And then I want to figure out the effective actions from that learned data, okay? We need to have two pieces of information. We have to have the noisy context before and after the user action. The action can be complicated, high dimensional. What we never did anywhere in this talk was to learn our latents, okay? It was great that they were there, but we never looked at them, okay? So that's the don't meet your heroes moment. The other thing is, we didn't try and generate all of W. I'm not trying to generate all of the emails that a user might see. All I'm trying to do is learn the conditional mean of the relevant features of W to predict what might happen when I do a new policy. That's a much simpler problem than modeling the space of all emails, right? So don't try and model all your emails, right? Just learn the features you need for the problem you're going to solve, okay? And finally, ridge regression is all you need. I did nothing in this paper but ridge regression, right? So yeah, you can solve everything without any diffusion models, any sampling, anything like that. Right, and so this work was sponsored by the Gatsby Charitable Foundation and Google DeepMind. So any questions? Thank you.